My name is Xiaofei Guo. Feel free to call me Rex. This is a work that a collaboration with my colleague Xueyang Wang from Intel. We both do security research at Intel, and we work on mobile and IoT security. So just before the talk, there's a disclaimer. We don't speak for our employers, and all the information here are our responsibility, including mistakes and bad jokes. So just before I dig into the details of the talk, I want to give everybody a high-level summary about what is the research about and what our solution is trying to solve. So as we know that malware development and detection is a cat and mouse game, right? The malware keep evolving and people try to write malware that are more stealthy. And traditional software level detection mechanisms, most of them relies on the correct functioning of the operating system. And there are some new approaches that propose that are based on VMM based detections. But then when you use VMM based approaches, you have a lot of semantic gaps. And there are ways to solve those semantic gaps, but it will incur a lot of performance overhead. So what we're trying to do here is to show you a new way to bridge this semantic gap, or even without knowing the detailed implementation of the operating system. And we're going to show you that by using the hardware performance counters, you can detect the kernel rootkit with very low performance overhead. And through the whole talk, I'm going to use kernel rootkit, specifically Linux kernel rootkit, to demonstrate the idea. But the idea is general, and you can apply it to other type of malwares. So here's the agenda of the talk. First, I'm going to briefly explain kernel rootkit, and then I'm going to talk about hardware performance counters. Then I'm going to explain our design, the Numchecker, and then how to use the design to detect and identify rootkits. And then I'll conclude the talk. All right. So since we're at Black Hat, I assume that most of the audience is probably aware of the general ideas of rootkit. Basically, it is a type of software that attacker injects into a computer, and then they use it to hide their activities from the user or the detection tool. And one type of rootkit that is very stealthy is kernel rootkit. The reason is that it directly affects the operating system kernel. So sometimes it can have unrestricted access to the system resources. Okay, and since you can do that, you can use it to hide the presence, open backdoors, gain root privileges, or disable defense mechanisms. And we classify the kernel rootkit behavior into two types. The first one is direct kernel object manipulation, also known as DCOM. This type of rootkit behavior basically subverts the kernel by directly manipulating the data objects in the memory. This kind of rootkit behavior has its limitation because it's only changing the data objects in the memory. And since it's only changing specific data objects, you can detect it relatively easier by checking those data objects in the memory. So another type of rootkit behavior is kernel object hooking. This type of rootkit behavior basically hijacks the kernel control flow. and compared to DCOM, it's much harder to detect it. And their studies show that a majority of the Linux kernel rootkit changes the control flow behavior of the Linux kernel. And that's why our research is mainly focused on this type of rootkit behavior. So if you see the diagram, it shows one example how the rootkit is going to affect your system. So for example, you have an application running in the user mode, and then it will trigger a syscall using the int 80 instruction, and then the execution will switch to the interrupt table, and then the system will look up the interrupt descriptor table, And then you will try to find which syscall it is by looking up the system call table. Now, if your system is not affected, you will execute the original syscall table and then execute the original syscall routine. But if you have a rootkit, it will try to give you a fake syscall table and then jump to a malicious syscall routine. Okay. So two specific examples of these rootkits. One is Socket rootkit. This rootkit basically gives you a fake syscall table. And another example is Adore NG rootkit. This rootkit changes the control flow at the virtual file system layer for some of the syscall routines. Okay, so we got this problem. Now, people have come up with different solutions. So the first solution is the host-based rootkit detection. The high-level idea is that the detection tool itself runs within the operating system. Now, and it periodically checks the kernel static and dynamic objects, right? But the challenge is that since the detection tool runs with the same privilege the detection tool runs the same privilege as the guest OS, the operating system. So if a rootkit has higher privilege, it will temper the detection process. So then people propose a different approach using virtualization. Now the detection tool runs at the VMM level, and it also the tool at the VMM level also checks the static and dynamic kernel objects. So this is good. It solves the problem of the privilege separation, but it also has its own challenges. So one of the biggest challenges is that it has semantic gaps between the external and the internal observation of the guest operating system. What that means is that it requires very detailed knowledge of the guest OS implementation. And people try to come up with different ideas to bridge the semantic gaps. But then all of these ideas so far will incur a significant performance overhead. So we propose Numchecker. It's also an architecture that runs at the VMM level, and it does not require detailed knowledge of the guest OS implementation. And the way we achieve it without knowing the detailed knowledge of the guest OS implementation is to validate the execution, the software execution flow using hardware performance counters. So the high-level idea is that you basically observe the hardware behavior from the software flow. You're checking the hardware behavior when you execute certain software programs. All right, so before I dig into the detail of Numchecker, I'm going to give a brief explanation of hardware performance counters. So the hardware performance counter, HPC, are also known as performance monitoring unit, and they're originally used for performance tuning. So to give you some example, both commercially available Intel and AMD CPUs have those counters. And those counters, each core has a certain number of counters. So, once you enable the counter will automatically start counting the events of the based on what you configure. And this typical events include counting the clock cycles, counting instruction retirement. Basically means how many instructions have been completed. Cache misses or TLB misses, right? And these events are very rich in modern CPUs. Both in Intel and AMD CPUs, you can find more than 100 hardware events that you can count. So I'm not going to jump into detail how to use the counters. If you want to know the detail, you can refer to the programmer manual. But basically, each counter can be configured to monitor any event that you like to see. Okay. So as I mentioned, our approach is VMM based. So the virtualization technology that we use in our experiment is KVM in Linux, but you can use other virtualization technology as well. Okay, but I will explain based on the KVM architecture. So KVM is basically based on the hardware extension from commercial CPUs. It has a guest mode and a host mode. Each VM is running as a process in the host. And KVM has a KVM kernel module, which handles the interceptions. It also has a Linux perf event kernel service. And this service basically helps you to initialize, enable, disable reads or close the HPCs. Okay, so we developed 3 different components on top of the KVM architecture. So the first one is the Numchecker kernel module in the host kernel. This module basically responsible for communicating between the KVM kernel and the performance event perf event kernel service. So the KVM kernel will notify when we should start counting and when we should stop counting. Okay. The second module that we add is the configuration program that runs in the user space. So because there's a limited number of counters on the CPU, but there are so many events to count, and if you count the number of syscall combinations along with the events that you want to count, there will be a huge number. So we develop a configuration program. You can turn on which syscall and event combination you want to count. And then the count value will be written to log files, and those log files are used to create reference models that we use to detect the rootkit. And if it is at runtime, we're going to use those log data to compare with the reference model. So I'm going to show you what that means. I'm going to show you the flow of the Numchecker design. So basically, it is a 2-phase detection and identification. It has an offline phase and it has an online phase, right? So in the offline phase, when you first deploy the system, the guest OS is clean. It's not infected by the rootkit, right? So the host will prepare to launch the Numchecker functionality. And what it does is that it logs into the guest and then execute a test program or a set of test programs. I'll explain what test program means. And when it launches a test program, it is going to, the kernel is going to monitor the hardware events. And then it will log the HPC reading results. Now, in the offline phase, the HPC reading results, we use it as a reference model. And then at the online phase, when we want to detect whether the system has a rootkit or not, we launch Numchecker, and then we monitor the syscall and the hardware event, right? By executing the test program. And then we log those results and compare with the reference model, okay? So this is a very high-level flow. There are several questions that you probably have. Well, the first one is, what is in the test program? How do we determine what's in the test program? And the second is, what kind of event and syscall should we select during the monitoring process? And also, how do we analyze the final results? So just as an additional note, in the online phase, besides launching the Numchecker from the host, you can also launch it from the guest. The guest itself can initialize the tracking process. So I'm going to show a detailed flow at the very low level, how we monitor different events when you launch the test program. So first you start the test program in the guest user space. And here, we're monitoring syscalls, but notice that I'm using an example instruction int 80 to enter the syscall, but there are also other ways to enter syscall, like sysenter or syscall. But here I'm just going to use this example as an example. So once you do int 80 instruction, you're going to trigger a trap to trap the host kernel. And this trapping requires specific configurations, depends on which processor that you're using. And it also depends on how you enter the syscall. If you're using syscall or sysenter instruction to enter syscall flow, then you will use different configurations on the CPU. Due to the time constraint, I'm not going to talk about exactly how to configure the CPU to trap the syscall. But if you're interested, feel free to come and talk to me offline. Okay, so once you trap the host kernel, it will initialize the performance counters. Now, after initializing the performance counter, the hardware will start counting the events. And the execution flow will go back to the guest kernel, and it will run the syscall routine. And then after the syscall finishes, again, we'll track the kernel, host kernel, and then disable the counter values and read out the counter values, and then redirect the execution flow back to the test program. So during the syscall process, there may be other high priority events that will interrupt the counting process, but there's no problem. There won't be any problem because we will store the counter value before we execute the interceptions. And then once the interception finishes, we'll restore the counter value and keep counting. So here's a very simple example for kernel preemption handling. Basically means one syscall interrupt another syscall. So while we're executing a syscall and there's another syscall coming and interrupt the current syscall, right? We'll do a task switch and then disable the performance counter. And then we'll execute the syscall that interrupt the current syscall. And then once that finishes, we'll do task switch back and we'll re-enable the performance counter. Okay, so now I'm going to talk about how do we create a test program. So first of all, once VMM launches the test program, it needs to know it is the test program that is triggering the syscall. So one criteria that we build a test program is that initially it has a preamble of syscalls that we choose. So the host kernel will monitor those syscall sequences and know that this process, it is the test program. Okay, and after the preamble syscalls, we're actually going to monitor the real syscall we want to monitor, the syscall that actually will be affected by the rootkit. Okay, so we'll have a set of selected syscall with control arguments in the test program, and then we'll set in a predefined sequence. Okay, so once we build the test program, as I mentioned, we choose the syscalls and the syscall argument, but we'll also need to choose what kind of event we want to monitor, right? So there are some principles that we use when we choose the event. First of all, we want to choose the event that occurs very frequently during the syscall execution. We don't want to choose an event that happens rarely during the syscall execution because that won't be very useful. And the second criteria that we use is that the performance counter reading will have noise. This is due to many reasons, because when you enter the performance monitor, when you start counting and when you finish counting, the processor will have those performance features that will have various number of noises during the counter reading. Right? So the second criteria is that we run through a number of experiments and we categorize the variation of those counter readings using statistical method. And then we find the ones that are more stable in terms of different executions. Okay, so the events that we selected in this talk are 5 events. First one is retire micro-ops. This basically means that micro-op basically means that when you execute a processor instruction, if it is a complex instruction set, you decode into simpler instruction sets. And the number of retire micro-ops are the number of simpler instructions that gets finished in the processor. Okay. And number of retire instruction basically means the number of complex instructions that are finished. The third one is retire near returns. That basically means how many near returns have finished. Near return means that when you return to the same code segment. And then the last 4 are related to branch. Return branch instruction basically means how many branch instructions that are finished. And return branch taken instruction basically means how among the branch instructions that are finished, how many of them have taken the branch predicted by the branch predictor. Okay, since we cannot avoid the noise during the counter reading, we need to characterize a noise threshold. We call it deviation threshold to quantify what kind of noise level is what we can is tolerable, right? So the way we compute the deviation is that we define the event EX. So EX basically means X basically means a particular event, right? And SY basically means a particular syscall. And the count C bracket, EX and EY, basically means that for that particular event and syscall combination, what is the counter value? Okay. So now, once we have this term defined, we can compute a reference counter value for a particular syscall and performance and event pair. And the way we do it is that we run through the syscall and the event. We run through it many, many times, hundreds of times, and then we average the values. Now, after that, we also run a few hundred different test executions. So each time we run the test execution, we use the deviation equation to compute the deviation. And from this set of results, we find that if you set the deviation threshold to 5%, then your false positive will drop to 0. Basically means that when there's no malware, you will classify all the event and syscall pair correctly. And so what that also means is that if you are executing the test program and you find that the deviation threshold, the deviation reaches more than 5%, that means there may be some modification happens in your kernel. Okay, so this is a very busy table. I will try to explain it very slowly. So the first column is the guest OS kernel version. In this case, it's a Linux 3.0. And the second column is the rootkit that we run on the guest OS. And the third column is the event that we selected in our experiment. Those are the same event that I mentioned earlier. So for each rootkit, we have 5 events. Okay. And the next 5 columns are the syscalls that we selected. Okay. And as you can see that we have 5 events for each rootkit and 5 syscalls for each rootkit. So altogether, there are 25 event and syscall pairs for the counter reading. And the numbers in the columns indicates the deviation when we run the test program. And the last column shows that whether the rootkit is detected or not. Okay. So as I said in the previous slide, if the deviation reaches more than 5%, regardless of which event and syscall pairs, we claim that a kernel modification is detected. So basically, if you see the red numbers on the screen, all the rootkit have at least one, or most of them has more than one, maybe 5, syscall to event counter values that exceed the threshold that we set. Okay. Now, if you take a more detailed look, you find that one of the syscall that all the 3 rootkits are trying to mess up with, that one is sysget DENTS64. Now, if you see what that syscall is doing, it's basically trying to return the file names under certain directory. And Linux uses that syscall to find out the PIDs by basically dumping the /proc directory. So you got a list of PIDs. Now, the reason why rootkit want to modify that is they want to hide the processes. So whenever you call that, you want to get the PIDs, they will change the syscall, and then you can see the actual process ID of the rootkit or some other malware. These are just some more data. We also did the experiment on Linux kernel version 2.6 with different type of malware. Same, you can see that there's at least one syscall to event pair that exceed the threshold. Okay. Same observation for Linux 2.4 kernel with other type of malware. So then I'm going to talk about some performance numbers. So we basically run the test program 500 iterations. We have a few test programs, basically 4 test programs. Each one contains a number of syscalls. So for example, if you see the first table, the first row, that test program contains a sysopen and sysclose. Okay, and you can see that the performance overhead it's around a millisecond range. Okay, and we also run some benchmarks, and we invoke the checking process during the benchmark execution. So we try 2 different periods. One is 5, one is 10. And the performance overhead is really small. As you can see, it ranges from 1% to 4%. All right. So sometimes that not only we want to detect the rootkit, we also want to know exactly which rootkit that is affecting our system, right? So we can try some ways to remove it or do some other detection or prevention mechanism. So what we do is that to identify which rootkit, we create what we call HPC-based behavior signature. The notations are similar. We have EX, basically means the syscall, the event, and SY is the syscall. And for a particular event and syscall pair, we have a counter value. And we count n number of hardware events, and we also count n number of syscalls, right? So, and then we basically create a vector of n times n entries, and each vector entry is basically a counter value. Okay. And then we use similar metrics to classify what should try to identify the malware. So the first equation is similar to what I showed earlier. It's a deviation equation. And then the second one, the d-test underscore max, is basically that when we run a number of tests, we don't compute the average, we find the max value, the max deviation value, right? And the last one is we want to compute, since now we have many points or many signatures for each rootkit, we want to know how similar two rootkits are when comparing those two vectors, right? So the way we do it is that we try to compare the deviations in each entry in the vector, and we try to see how many are within the threshold deviation. Okay, so we run some experiments, and basically what you can see is that so the rows are different rootkit types, and the column are also different rootkit types, and maybe I can use a pointer. Never mind. There's mouse. Okay, so what you can see is that if the deviation is low between two rootkits, that means they are the same rootkit, and the threshold that we set is 5%, same as in the detection flow, we set it as 5%. So if we compare two rootkits, their deviation is smaller than 5, we say they're the same rootkit. And if the deviation is bigger than 5, we say they're different rootkits, right? So you can see that the same rootkits, their threshold all falls below 5. And another indicator you can see is the vector comparison, the fitting rate. So if the fitting rate is 100%, that means all the points fits together, meaning all the event and syscall signatures fit with each other, right? So if it is a different rootkit, for example, this one, you'll see that the fitting rate is really low. Okay. So one important thing to notice is that there are two rootkits. One is socket, one is superkit. We find that their deviation is quite similar, and their fitting rate is also relatively high, right? So for socket and superkit, the deviation is very, very close to our deviation threshold. So at that point, it's really hard to distinguish whether the rootkits are the same or not, right? And that fundamentally related to their behavior. Their behavior may be similar, but there should be a way to tell the difference between this rootkit. So what we do is this. Instead of getting the event count at the end of the execution, we try to sample it periodically. Now, if you see this demonstration diagram, although if we sample the counter reading at the end, the malware 1 and 2 will have the same reading. But if you sample it periodically during the execution, you will find their reading are actually different. Okay, so what that means is that, first let me explain what all this diagram is about. Each row, it is a syscall execution, and each row contains 4 events. So for this syscall, we record 4 events. Okay, and then there are 5 syscalls, and each syscall contains 4 events that we monitor, right? And the blue line here means malware 1, well, rootkit 1, and the red one means rootkit number 2. So in this case, the blue one is the socket, and the red one is the superkit. So now you can see that if you look at their behavior over time, you can see the difference among different event and syscall pairs. Okay? So remember, in the previous way we calculate the deviation, we use the counter value. So now we don't use the counter value. What we use is that the area of the curve, we compute the area of the curve over x-axis, right? So for these two malware, the area will be different. And we use that to compute the deviation. Okay, so the first table is the result when we have no periodical sampling. as you can see that the deviation is very close to the threshold. And the second one is when we add periodical sampling, right? You can see that we can significantly distinguish these two rootkits. So before I conclude the talk, I also want to talk about security analysis of the scheme. I mean, it's all good that we detect the rootkit, it's all good that we identify the rootkit, but I'm pretty sure in this cat and mouse game, the rootkit writer is trying to bypass the scheme if they know the scheme exists, right? So start from the weakest attacker, right? The weakest rootkit may try to tamper with the performance counters, but then this is not possible because performance counter in the CPU, they support full control in the VMM. So the next type of rootkit, they may try to tamper with the analysis program. This is also not possible because our analysis program is in VMM. The rootkit will also try to predict the good numbers, right? So what that means is that they try to create modifications that when we read the event value, it is the same as the good number, the number that we're looking for, right? So in our scheme, we have an assumption that you can use test program as a secret key. The reason we say that is that the test program you can design in so many different ways because of the large number of system call arguments and events. You can create a huge number of different test programs. Now, even if the rootkit try to guess one of your test program and they figure out the good numbers, you can always update your test program. All right. Those rootkits that I just talked about are pretty, probably too weak. Now we see stronger ones. So this type of rootkit may try to undo the modification, right? Now, if the rootkit who try to undo the modification does not know the test program exists, then it does not know when it is being monitored, right? So even if you try to undo the program, maybe it is during the time that it's not being monitored. So that's not very useful because eventually we'll catch it. Now you may also try to identify the test program, which is very reasonable. So as I said, the VMM can update the test program and try to use other ways to evade the detection from the rootkit. So let's say the rootkit detects the test program and it tries to undo the modification, right? Now, if we simply undo the modification, it's going to get into a dilemma because its whole purpose is to hide other malicious activities. Now, if it doesn't undo, we'll detect the rootkit. But if we undo and we have other detection mechanisms, we'll detect the other activities. So it puts the rootkit into a dilemma. And also, to make the detection really hard, you can also randomize the sampling period. Now, finally, we don't eliminate the possibility that the rootkit is really strong. And the rootkit can detect the test program accurately and undo all the modifications, right? What that means is it undo the modification in the kernel, it reads all the activities on your system. That's also possible. If that's the case, then what we suggest is that we should not use a test program, right? Rather, we should go for a different approach where we use machine learning algorithms to actually classify the correct behavior of the system and then create a sort of whitelist machine learning model to check whether your system is infected or not. How are we doing on time? Okay, so in conclusion, we propose this Numchecker idea. Basically we showed that it can effectively detect and identify kernel rootkit. It is a VMM-based framework. So although we use KVM in this talk, but you can use any virtualization technology you like. And because it validates the execution of the guest syscall, you don't need to know the detailed implementation of your guest OS implementation. And also, you're not necessary to monitor the syscall. You can also monitor other software behaviors on the system. And the good thing is that all these events are supported by hardware and by commercial CPUs today. And the performance cost is really low by using these performance counters. And finally, what we want to say is that we use Rootkit, kernel Rootkit as an example, but you can really use it for other type of malware. Depends on how you identify the behavior and use the events to characterize those behaviors. All right, so finally, I want to thank these people who give the reviews. All these folks are from Intel. And with that, I finish the talk. Any questions? Yes. Okay, so the question is, when a good program triggers the syscall, whether the detection mechanism will have a false alarm, right?
My question is that if I apply this technique onto the normal system, there would be cases where the benign programs will also have the similar behavior.
Okay, so that's not the case, because the way we're checking it is that first you create reference model based on a clean system, right? And once your system is not clean, meaning once your kernel is being affected, then no matter a good program or a bad program calls the syscall, the detection algorithm will say modification is detected. And also one thing, in our experiment, we only trigger the detection mechanism when we execute the test program. But if you want to do it with a normal program, you can also do that.
Okay. So
does that answer your question?
I'm a bit, yeah, I think yes, but another question is like, will the benign programs will have uniform counter values for the similar system calls?
Would the benign program will have uniform values?
Uniform counter value, performance counter values.
Uniform, what do you mean by uniform?
I mean, when you are checking these branch instructions or microbes, so will that counter value be uniform across the same system call but for the different programs?
Oh, okay. No, it won't be the same.
Because you are looking at the deviation when you are when you are trying to find the rootkits, right?
Right.
So will that be a uniform? If it is not uniform in the benign, then the benign program can also be suspected as a rootkit.
Yeah. So here's the thing: the counter reading for a particular syscall, excuse me, and hardware event won't be uniform because there's a third variable that is the argument to the syscall. So different benign program or malicious program, they will try to call different arguments to the syscall, right? Now, the way we select our test program with fixed argument or a set of argument that we want to select to trigger the syscall and event counting is that we analyze the malware behavior, because in the syscall there are certain number of areas that you really want to modify to really hide your process or files or whatever you want to hide, right? Now, as long as the argument that we selected can cover those flows that the rootkit is trying to change, then the rootkit will get detected.
Okay. Okay. So another question is, does the counter also take into account the event of the other processes, or it's based on you're monitoring for one single process?
Yeah, so so in the virtual machine, the counter readings are isolated at the process level. So you don't need to worry about process isolation. Yeah.
Okay. The one last question.
Yeah, go ahead.
Because the hackers always try to find new ways to build the rootkits. So they might try to obfuscate in a way that the counter values are randomized, and then you will not find the significant difference between the deviation which you are looking into.
Well, as I explained in the security analysis, right? If he just randomized the counter value, it doesn't do much use for him, because if it is randomized, then it will exceed the threshold at some point. The thing that is really useful for a rootkit writer is to make sure the modification actually align with the good number.
Yeah, but I may put a modification along with my some random codes so that it doesn't make the difference so visible at the counter level.
No, if you write random code, then you need to make sure your random code don't exceed the threshold.
Okay.
You need to really make sure that as long as whatever random code you're writing, as long as it exceeds the threshold, then the malware is detected. But the smart rootkit writers may try to write their modification such that it is aligned with the good numbers. But as I said, you can also update the test program. You have a huge number of arguments, syscall, and also hardware event to select. So it's going to create the rootkit writer's job much harder.
Okay. Thank you.
One question.
Yep.
Would it be possible for a rootkit writer to actually detect that Numchecker is available and just because Numchecker has to visualize the performance counters and to stop and start check starting the performance counters and then detect that it's running in such an environment and just skipping all its work, just removing this stuff from memory?
Yeah, that's a good question. Actually, I explained those in the previous slide. Maybe I go too fast, but let me answer your question. So I classify into different cases, right? The rootkit may try to identify the test program, right? Is that the scenario?
Not the test program itself, but the fact that when you load is using Numchecker.
Okay, sure, you can detect that.
It's available in the ENM below.
Sure.
As soon as they figure out that my system calls that I'm executing within the rootkit, something taking a little bit longer maybe because Numchecker has to do some work at the beginning and the end, what I can read, then I would just remove it from memory and you will be able to take it.
So yeah, that's a scenario, but you will modify the syscall at some point,
Yeah,
right? How are you going to execute the syscall? You modify at some point, and you will execute it. The moment you execute it, then there's a possibility that it will get detected. We're not saying all syscall, all the modification will get detected exactly at the time that it gets modified, right? So yeah, that's a valid scenario, for sure. But it also requires the rootkit writer to know when you should undo the modification. Right. Hi, yeah, go ahead. Not really, because performance counter record really low-level hardware events. So, for example, the one that we choose, the number of operations, micro operations that are completed, that really depends on your program. I mean, you can configure the system differently, but once you configure it you build your reference model. Okay, so is the question related to that when during deployment you change your operating system, part of your operating system, will that affect the reference model, right? So we haven't done a detailed analysis on that, but the possibility definitely exists. Depends on what part you're changing the operating system. Yeah. And also depends on what event you're monitoring. Go ahead.
One more question. Are you proposing that for production systems or just for the lab environment where I want to analyze suspected malware or something? Or should this run in the production environment?
Should this run in production environment?
Yeah, to just always online monitor your systems while they are.
Oh, I see. You can do both ways, but I think the real benefit of this is that the performance overhead is much lower than pure software solutions. So you can actually run it online. Yes.
You mentioned machine learning at one point in one of the slides that when the, yeah.
Which one?
No. Well, in one of the slides that you talk about what the rootkit can do, and then how rootkit can actually try to counter this.
Oh, okay.
program.
Security analysis. This one? Or the next?
No, secret key. No, there is a slide. Yeah. So strong with the last point. So have you done something on that work? How you actually approach this machine learning?
So we are very interested in doing this research. But we can't say any result for now. But yeah, I think that this direction is possible. If you're interested, we can talk offline if you want to collaborate on this. Yes. Any other questions? All right, I think everybody's ready for lunch. Okay, thank you for coming to the talk again.